Physics, electricity, part 1. I did open it, didn't I? Yeah. You saw me pick this? There we go, I did. Okay. Got that charging current. Okay. So from chemistry, you already know, or even just from middle school, you already know that electric charge is a property of electrons, protons and other particles. And electrons are negatively charged, and protons are positively charged, and neutrons have no charge. So, I'd say you definitely know this. Things that are negatively charged and things that are positively charged attract each other. So this makes electrons and protons stick together to form atoms. Things that have the same charge push each other away. They repel. This is called the law of charges. Now you probably already know that, but maybe you didn't know the name, or I don't know. If you can make some notes on this, you don't have to write the whole thing. You wrote something? Yeah. Yeah, got that? Lee? Yeah? Okay, good. Right. Next. Okay. So, basically, you might have heard this word, I doubt you've heard it in chemistry, current. Do you talk about currents in chemistry? No. So a current is just a flow of charge. In a metal, it's the free electrons that flow. And I know you did that in chemistry. Who have I got? Bruce. Did you get wet? You wet?
What?
Wet! W-E-T.
What?
Oh, never mind. Never mind. Never mind. It's terrible, isn't it? Terrible. You know from chemistry that it's the free electrons in a metal that, that metal has free electrons. That it's these that flow. And here's just a very simple picture of what's happening. Oops. I think it would be good if you can draw the picture with the definition here. We have the same yellow vest. Do you cycle?
Yeah.
You cycle today?
Yeah.
Good man. I'm proud of you. How long is your cycle?
20 minutes.
20 minutes in the rain.
Okay.
You need some forage. Okay, did you draw that? Yeah, this is familiar to what you do in chemistry, right? Yeah. Okay. So next now. Bruce and Chu, you got your notes ready? I'll let you write this down and then we'll continue. Did you draw a picture of this as well? Yeah. Okay. Got that, Bruce? True? Come on, Bruce. Oh, Bruce, come on. I won't wait any longer. An electric current is a flow of electric charge. Yeah. 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 Now.
Yeah.
Okay. Now, have you ever heard of an electrolyte? You've heard of that? What is it, Monica? Yes? Good, yeah, yeah. An electrolyte is a liquid that can conduct electricity, but what is carrying the charge when the charge moves through it? In the metal, it's the electrons.
Acid.
But acid doesn't have a charge. Not just negative ions, but just ions, I think. An electrolyte is a chemical that conducts electricity. It can carry a current. It's actually what's used in batteries to make the ions flow, producing a current. And if you didn't know what ions are, which I hope you do know, ions are just atoms with an extra electron or a missing electron, therefore making it negative or positive. But you know that. Yeah? So you just need the first sentence here, as long as you know what ions are. If you don't know what ions are, I will tell Lorraine on you, and you'll be in big trouble. You've done ions in chemistry at this point, haven't you? Yeah. Now, I won't really talk about this picture, because this isn't really on our physics course. And in some ways this is nearer to chemistry than it is to physics. Do you do this in Lorraine's chemistry? Have you done it? No, but you remember doing it in chemistry? Yeah. So just the first sentence here is enough. An electrolyte is a chemical that conducts electrical current. It's used in batteries to make the ions flow, producing current. Got it? Yep, great. Okay. Let's look at what's next now. So, which way should we say the current flows? So, I have a little picture here. Here's a battery. Here's a light bulb. Here's a switch. So, should we say the current flows from positive to negative? Or maybe we should say from negative to positive. Or which is it? No.
Positive. Oh. The electric.
Yes.
From nothing to.
You said both, didn't you?
Yeah.
Yeah, correct. It is a bit complicated. It's a bit complicated. Just wait, I'll explain. So what we say, we say the current flows from positive to negative, but actually what's happening is the electrons are flowing the other way, negative to positive. So you have to be careful with your English. The current flows from positive to negative, but the electrons are moving from negative to positive. So, kind of both. Depends on the English. Be careful with this, okay? So if I said, which way are the electrons flowing? Negative to positive. Which way is the current flowing? Positive to negative. So I think I might have this on the next slide. Yeah. So this is what's happening here. The electrons flow, as you can see, from negative to positive, but we say the current flows. Conventionally, the standard is the current, we say it flows from positive to negative. So yes, Lee, both. Now, continue? Yeah. So, now just to be super clear, if an electron moves from A to B, we say there's a current flowing from B to A. Yes, B to A, not A to B. Okay, so if the electron moves from A to B, we say the current flows from B to A. That's not a mistake, that's how we say it. Yep, okay. But you might be saying, why? Why can't we say the current flows in the same direction as the electrons? What's the problem with this? Well, the reason is electricity was discovered before people knew what protons and electrons were. You must understand, when we call something positive and we call something negative, it doesn't actually matter. It's only a word. We can call positive negative and we can call negative positive. As long as everybody does that everywhere all the time, that's fine. I'll give you an example. This is my left hand, this is my right hand. If I swap the words left and right, and if everybody does that, then we don't have any problems. Nothing is lost. Everybody understands what left is, everybody understands what right is, and we understand left is opposite to right. It's the same with charge. When we call something negative and we call something positive, it's not really negative, and it's not really positive. It's not really -1, it's not really +1. There's a difference. That's all we care about, that one is one and the other is the opposite. So actually, if this blows your mind, we could be calling electrons positive, and we could be calling protons negative. And in fact, that would be better, because if we called electrons positive and protons we called negative, then when the electrons move, they move in the same direction as the current. We can then say an electron from A to B is the same as a current from A to B. But we don't. And the reason we don't is because of Benjamin Franklin. You might know him as the guy who likes to fly kites in bad weather. Yes. Because we call electrons negative and protons positive, this is the problem. It'd be better the other way. I always find this comic funny. So what's happened here is in Benjamin Franklin, when he did the experiment with charge, what was left on the plate, he just called that negative. Now what was left on the plate, he should have actually maybe called positive, because it would have made things nicer later. But it doesn't matter, it's just something to keep in mind. The language, it's only language. What we care mostly about is that they're opposite signs. Yeah. You can look at this comic in more detail later. What else do I need to say about this? Oh yeah, so just to be clear, this isn't true about everything. So for example, my bank balance, if it's negative, it really is a negative. What? It's not that funny, is it? Really that funny? Okay. Anyways, it's not like I can do this with my bank balance. If my bank balance is negative, it really is a negative number. It really is -1, so I should call it negative. So it's just a language thing. Okay, so now we need to define something here. Now this definition is very technical. Unfortunately, this is the official definition of an amp. Just before I do that, you know, as we said earlier, the law of charges means that like charges repel. So imagine we have a wire here and a wire here, and let's say, I don't know, we'll just say this is a positive, well, we'll call it an electron. An electron moves up here, and an electron moves up here. If these wires are near each other, what should they feel? There should be a force pushing them out. And if you don't want the wires to move, then you will need another force here to pull them back. So you can imagine that you put something in between these wires to measure the pull-in force to keep them together. Yeah. So we say we have 1 amp of current if the attractive force is equal to 2 times 10 to the minus 7 newtons per meter of wire, which are infinitely long, really, really tiny, and they're 1 meter apart. So in other words, if I make this 1 meter apart, then the force I require here to keep them balanced, in other words the F, that needs to equal 2 times 10 to the minus 7 newtons. If I have this much force between them, then I have exactly 1 amp flowing through it. Now this, I said, is a very, very technical definition. If you can remember the picture, it will help you to remember the definition. So the picture is like this. You have a wire, and you have a wire, and these are 1 meter apart, and the radius here is nearly 0, and the wires continue to infinity. And you need a force to keep them together because they want to bend out. They're trying to move this way. Or if you do it the other way around, if you have one current flowing this way and the current flowing the opposite way here, then instead of pushing apart, they'll want to pull together. Doesn't really matter. The key thing is that the force between them, either pulling or pushing, the force here needs to equal 2 times 10 to the minus 7 newtons. If you have this, then we say we have 1 amp. And the current here and here needs to be the same, 1 amp. Now I'd like you to write this down. I don't expect you to remember this perfectly in the exam, but if at least you can remember the picture and try your best to explain the picture, then you've got a good chance of getting it. It's a very technical definition, very technical. Okay, do you have that? Not yet. Got that now? I still see people writing. Ready? Great. Okay. Here's a picture of when they're flowing together. Okay. So, anyways, I might have had my arrows backwards. Not that it matters, because we just care about the force. Anyways, now we can go on to the next definition, which is the Coulomb. So the Coulomb, I don't think you do this in chemistry, but the Coulomb is what we use to measure charge. So for an electron this will be negative coulombs, and for a proton it will be positive coulombs. And we define the Coulomb quite simply as the Coulomb, which we have a letter C. It's the standard unit for charge, and it's defined as the charge you get by a current of 1 amp in 1 second. So you have 1 amp, you leave it on for 1 second, a total of 1 coulomb has flowed through it, the circuit, to the conductor. Or as a formula, actually, it gives you this, that the total charge is equal to the current multiplied by the time, where Q is the total charge, I is the current, and T is the time. So 1 coulomb is 1 amp per 1 second. Now I'm not actually saying the full name. What is the full name for amp? You can actually see it on the top of the slide. Ampere. Which sounds like what language? It's not English. Ampere. Greek? Come on, dude. That is not Greek. Might be sounding a bit French, perhaps. You know, I'll have a pain au chocolat, a croissant, and an ampere, please. The total charge transported. Got that? Formula and definition. I will say this is one of the common definitions on the exam for electricity. What is a coulomb of charge? Yeah? Now, using coulombs, I can tell you things now. I can tell you how big a coulomb is. In fact, a coulomb is actually a lot of charge. If you compare this with, say, an electron, how many coulombs of charge does an electron have? Not much. One electron has a charge of minus 1.6 times 10 to the minus 19 coulombs. which we often just write as E, and that's not actually true. I should have written as a minus E, I think. Who has the Casio calculator? Monica? Can you type in shift 723? Do you get a value of E? Is it 1.6? Is it plus or minus? Plus. Yeah, okay, so that's a typo. I should have written minus E. If you can just... I'll fix that. That's a minus E. Or what you call in chemistry minus 1. Because I'm sure when you're doing charge with Lorraine, you call an electron minus 1 and a proton plus 1. Whoops, sorry. Come on. If you're writing this down, please note it's a minus E.
Why minus 1?
That's what you call it in chemistry, isn't it? You say charge of an electron is, and this is why I have it in quotes, minus 1. I don't have any units though. Yeah? But just so you know, this value is on the calculator. If you have the Casio one, I think it's shift 7 and then 23 is this number. Does that have it?
Minus constant 23.
Yours puts it in as a minus.
What?
The screen result?
Is a plus.
It's a plus, yeah. So it's minus E is the value. Yeah, let me just fix that down here. Minus E. Okay, continue. Yeah? Yes? Let's have a look at an example. I think this is quite straightforward for you to do. You have 100 milliamps flows through a copper wire for 2 seconds. What's the total charge? So we have our copper wire and flowing is 200 milliamps flowing through it. So we have some charge in total that has travelled through it. So how much charge has travelled through it? Well, that would be IT, which will be 0.2 times 2, which is 0.4 coulombs. 1. So that is 0.02, or in other words, 20 millicoulombs. What the heck am I doing? 0.2. 0.2, which is 200 millicoulombs. That's it. Did you write that down, Bruce?
No.
Would you like to write it down? Yes. You should. I recommend you do.
100 equal 100 milliamps.
1000 milliamps. I see a couple of people write and then we'll go on.
We have to use Coulomb.
Say again?
For units. Can you write like milliampere, etc.?
Yeah, you could. Because you have Q equals IT, then a Coulomb is the same as an amp second. But this isn't the normal way to write it. It would be more normal to actually write amp if you wanted to as a Coulomb per second. Okay, got that?
Yeah.
True? Okay. Now, before I give you the worksheet, I just want to give you wonderful. For you, I reprinted the materials worksheets. They all have the answers if you want to check your work, and also they all have the links to the videos as well if you want to check. So if you can take one and pass it along. We're missing Sean and Jerry. Bruce, can you keep one for Jerry?
No.
And who can keep one for Sean? And Chrissy, can you keep one for her? Who will see Sean later today? Yeah? Then you can keep two. You have two, Bruce? One for you, one for Jerry?
Yeah.
Yeah? You should have three. Yeah. Okay, all good? Oh. No. I don't have any left. Does anyone have two?
I have one.
We have 9 students, don't we? I printed 9. Can you double check nobody has 2? Bruce, you should have 2.
Yeah.
You don't have 3. KJ, you have 1?
One.
Dude, what happened?
I have nothing.
What do you mean you have nothing? You literally have it in your hand right
I
now.
mean the question for
No, I haven't given you that yet.
Oh.
That's for materials. So you have 1, you have 1, you have 1. Bruce, you have 2. Lee?
I have 1.
And Monica?
2.
Alright, I don't know what happened. I'll deal with them later. Okay. Oh wait. Some reason it went to the back. Okay, you need 1 more, please. Thank you. Okay, let's see. Okay, so we're just looking at the first worksheet. I'll let you try this for... No, you don't have it yet. I'm going to give you 2 electricity worksheets for today. The first one is charge and current. These questions you can see are quite easy, so you should be able to do them in a few minutes. 1, 2 and 3 are straightforward. 4 is a bit difficult, but 1, 2 and 3 are so easy it's only fair. Okay, so if you can open this up and go to the first worksheet and try those questions now. I think it should take you like 5 minutes, maybe 5-10 minutes. Yeah, everybody has one. You're going to take me 2 more. And then Bruce, you're going to take one for Jerry. Yeah.
What is change in the mean temperature to seconds?
10 to the minus 3. Is that the first question? Or my example?
Yeah.
The first one. Looks right. Is my answer wrong? My answer's on the next page. Right? My answer's right or wrong? Can I see? What did I ask you to do? No. The 1 hour is 3,600 seconds.
Oh.
And also this is 2 amps, not 0.2. It's 2. So the current is 2 and the time is 3,600. Which one are you on, Lee?
Number 4.
Yeah, why not? Because you have the number of electrons, so just divide by Avogadro's number, and that's how many moles of electrons you have.
But it doesn't ask me the question.
Oh yeah, so you don't have to give it as moles, it's convenient. When you're counting something that's very, very large, it's convenient to use moles because Avogadro's number is very large. So rather than saying, I have 6 times 10 to the 23 active electrons, it's more convenient to say, I have a mole of electrons. So how many moles did I have here?
0.01555.
That was my answer?
No, 0.0155.
Yeah, moles. Rather than writing down whatever times 10 to the whatever. Just divide by Avogadro's number, yeah. But Monica, you can leave your answer the way it is. It doesn't need to be in moles. Take my answer and multiply by Avogadro's number. See if it's the same as what you got. How are we doing in number 4?
No good.
That was a quick answer.
Yeah.
Have you done any part of it?
No.
Interesting.
I wrote down Q equals to 1, 1, equals to 1 column and 1 stop.
How about you watch the video? So I have the link there. And I'll go get a cup of coffee, then we'll come back and start the next lesson.